Let's continue talking about photons and electrons. Remember, we talked about the photoelectric effect, where a photon can hit a piece of metal and eject an electron. And there needs to be a certain frequency associated with a photon, but the amplitude didn't matter. So one photon at that threshold frequency can give the electron just enough energy for it to escape the atom. When there's more energy given than that needed binding energy, that extra energy becomes the kinetic energy of the ejected electron. So the kinetic energy of our ejected electron is going to be the energy of the photon minus the binding energy. So the binding energy is the energy needed for it to escape, and the energy of the photon is the total energy transferred. So if you take the photon energy minus the binding energy, you get the kinetic energy of the ejected electron. So let's think through this question. Suppose a metal will eject electrons from its surface when it is struck by yellow light. What will happen if the surface is struck by ultraviolet light? No electrons will be ejected. Electrons will be ejected, and they have the same kinetic energy as those ejected by yellow light. Electrons would be ejected, and they would have greater kinetic energy than those ejected by yellow light, or electrons would be ejected and they would have lower kinetic energy than those ejected by yellow light. Well, ultraviolet light has a higher, a shorter wavelength, a higher frequency than yellow light does. And so our binding energy is going to be the same, but the extra energy is going to be greater than those with yellow light. So the correct answer is C. We have more energy associated with those ejected by ultraviolet light than those ejected by yellow light. When atoms or molecules absorb energy, that energy is often released as light energy. So that is the energy has to go somewhere, and often it goes into light. So we can shine that emitted light through a prism, and we will see particular wavelengths of light that are unique to that atom or molecule. It's called an emission spectrum, and it can be used to identify the material. The example here is flame tests, which are where you put typically a metal into a flame and it gives off a characteristic color. Here are more examples. These are neon, technically only this one is neon. These are bulbs filled with noble gases, and if you add energy to them, they emit light or electrical. When they're excited with electrical energy, they emit light. And then here's the flame test. You can see that different metals give off characteristic colors. So sodium glows orange, which is why if you've ever had a pot of water for pasta that you added salt to boil over, it turns the burner on your gas stove orange. That's from the sodium. And then potassium's purple, lithium's red, barium is kind of a yellow. And here's the emission spectra I was talking about. So if we excite hydrogen ions here in a hydrogen lamp, run it through a slit and then through a prism to separate out the wavelengths, we get just these characteristic wavelengths of light being ejected. So only photons with a certain wavelength are emitted when an atom or molecule is excited. Here's another example. So white light, we get all of the wavelengths. Helium, we only get these certain wavelengths emitted. Barium, oxygen, neon, you can see as we have more electrons associated with a atom, there are more photons of different wavelengths being ejected. Okay, so Rutherford's model of the atom had electrons as these moving charged particles moving around a central nucleus. So according to classical physics, if we're back in macro territory, moving charged particles give off energy. So if that's what's happening in an atom, electrons should constantly be giving off energy, causing things to glow, which then causes the electrons to lose energy, crash into the nucleus, and which should have the atom collapse, but that is not what happens. So we need a more robust theory of the atom. This leads us to the Bohr model. So Bohr developed a model that explains how the structure of an atom changes when it undergoes energy transitions. So the big idea here is that the energy of the atom is quantized. The amount of energy is related to the electron's position. So, and according to the Bohr model, atoms can only have very specific amounts of energy related to those spectra that we just saw on the previous slides. So electrons only have specific amounts. It's not a continuum of energy. It's quantized. Now in Bohr's model, his model looks kind of like a model of the solar system, where you have the nucleus in the middle and then electrons traveling in orbits at fixed distance from the nucleus. And then when electrons jump from one state to another, or from a higher energy down to a lower energy, that difference in energy level is emitted as a photon of light, and that is what causes those lines in the spectra. So electrons have these quantized amounts of energy. They can jump up in energy and then back down when they jump. So the jumping up in energy is from an external source. When they go back down, they emit a photon of light with that certain amount of energy relating to the distance between the energies emitted. So here's a better picture than the one I just drew. So you have the nucleus here. You have these different sub-levels, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. And say when an electron jumps from n equals 5 down to n equals 2, that distance in the that difference in energy in a hydrogen atom corresponds to a photon with a wavelength in the violet range. From n equals 3 down to n equals 2 corresponds to a wavelength in the blue-green range. 3 to 2 corresponds to one in the red range. So Bohr's model gives us an explanation of the spectra that we see, but it's still not robust enough to explain all of the different pieces of data that scientists would collect.